Have you ever stopped to think about how your phone, your laptop, even your smart TV finds anything on the internet? I mean, it's this massive, sprawling network. So today, we're going to decode the digital address system that makes it all work.
So let's start with a really simple question. You type a website into your browser, you hit enter, and then what? What's happening in that split second? How does your request possibly navigate a sea of billions of devices to find the one single server it's looking for?
Well, the answer is pretty much the foundation of all online communication. See, for any of this to work, every single device connected to a network needs its own unique identifier. It needs a digital address that basically tells everyone else, hey, this is who I am and this is where you can find me.
And that address? It's called an IP address, which stands for Internet Protocol Address. It's a unique numerical label, and I mean unique. Every computer, every phone, every server gets one. It is the fundamental way that devices find and talk to each other online. No IP address, no connection. It's that simple.
The easiest way to wrap your head around this is with an analogy we all get. Just think of an IP address as being exactly like a physical home address that you'd put on a piece of mail.
So, sticking with that home address idea, an IP address really breaks down into two main parts. First, you've got the network part. That's kind of like the street name. It tells you which digital neighborhood the device lives in. Then you have the host part. That's the specific house number on that street. You absolutely need both to get the message to the right place.
But here's where it gets interesting. Not all IP addresses are created equal. As the internet just exploded in popularity, we realized our original system was, gonna run out of addresses. This led to two totally different generations of IP, the classic version and its much, much bigger successor.
The original, which we call IPv4, is a 32-bit system. That gave us about 4.3 billion addresses. Now that sounded like a ton in the early days, right? But with smartphones, laptops, and all these smart devices, we burned through them way faster than anyone imagined. So we had to invent IPv6, a 128-bit system. And the number of addresses it provides is, it's just staggering.
Yep, that's a real number. It's 340 undecadillion. It is so ridiculously large, it's hard for our brains to even process. This basically ensures we have more than enough addresses for every device on Earth, and probably every grain of sand too, for a very, very long time. This is what makes the true Internet of Things possible, where literally everything from your fridge to your shoes can get its own unique spot online.
Okay, so we've got tons of addresses, right? But here's the thing. They're not all used in the same way. There's a really important difference between the address your device uses out on the public internet versus the one it uses inside your own house. Let's break that down.
So here's the deal. A public IP is your globally unique address. It's your face to the entire World Wide Web. Think of Google's famous 8.88.8. But a private IP, that's only used inside your local network, your home, your office. It lets all your personal devices chat with each other without being exposed to the whole internet.
And you've totally seen this before, even if you didn't know what it was. Ever poked around in your Wi-Fi settings and seen an address that starts with 192.168.1-something? That's it. That's your router, acting like a little traffic cop, handing out these private addresses to your phone, your laptop, your game console, so they can all talk on your home network.
Now, what happens when things get bigger? I mean, way bigger, like a huge corporation. You can't just have one gigantic street with thousands of houses on it. That would be absolute chaos. So this is where we have to go from thinking about a single street to creating entire organized digital neighborhoods.
And the process for doing that is called subnetting. It's a really clever technique of taking one big network and just logically chopping it up into multiple smaller, more manageable little networks, or subnets. Think about a large company, right? You absolutely do not want the folks in the sales department to have access to sensitive HR files. Of course not. So subnetting lets the company create these separate, isolated networks for each department. They're all still part of the bigger company network, but they're kept in their own lanes. It's all about organization and, more importantly, security. So why go through all this trouble? Well, the benefits are huge. For one, it's a much more efficient way to use your IP addresses. It also cuts down on network traffic because most communication stays inside its own little subnet. It seriously boosts security by keeping things separate. And honestly, it just makes the whole system so much easier for people to manage. Okay, so that's the what and the why.
But how do we actually do this? How do you tell a network where one of these neighborhoods ends and the next one begins? Well, for that, you need a couple of special tools.
The main tool for the job is the subnet mask. It's another 32-bit number, and it works hand-in-hand with an IP address. Its only job is to put a mask over the IP, telling the computer which part is the network, the street name, and which part is the host, the house number. That 255.255.255.0 is one you'll see all the time.
Now, typing out 255.255.255.0 over and over is a little clunky. So network engineers came up with a much cleaner shorthand called CIDR notation. Instead of that long number, you can just write /24. It means the exact same thing, that the first 24 bits are for the network. It's just a way cooler, more efficient way to say it.
All right, let's put it into practice. Imagine our goal is to take one standard /24 network and split it into 4 smaller equal subnets. The math is actually pretty simple. To get 4 different options, you need to borrow 2 bits from the host part of the address. Why? Because 2 to the power of 2 equals 4. So we add those 2 bits to our original 24, and our new network prefix becomes /26.
And voila, check this out. That one big block of addresses is now neatly divided into 4 distinct subnetworks. Each one has its own specific range of IPs, and each can be managed on its own. We've basically created 4 organized little digital neighborhoods from one big piece of land.
All right, let's do a super quick-fire recap. The IP address, that's your device's unique ID. The subnet mask, that tells you what's the network and what's the host. CIDR, that's the cool shorthand for the mask. Public IP is for the whole internet, and private IP is just for your local network. Got it? Good.
If there's just one thing you remember from all this, let it be this right here. An IP address gives every single device its own unique identity. But it's subnetting that gives our massive, complex networks the organization and the structure they need to actually work properly and securely.
So that's the blueprint of how our digital world is organized, and it leaves us with one final fascinating question to think about. Now that you get how these networks are built, and you know we have a practically infinite supply of addresses with IPv6, what kind of new possibilities does that unlock? What happens when literally everything can have its own address on the internet? Something to chew on.